Okay, well, good evening, good morning, wherever you are, everyone. This is the SETI Game Changer Seminar. My name is Mark Sargent, and I'm the SETI Science Program Manager. I'm going to be your host today for the third talk in this series on habitability from galactic to microbial scales, and it is our pleasure to welcome Professor Jill Tarter for this presentation. So Jill is Emeritus Chair for SETI Research at the SETI Institute. SETI Institute being located on the west coast of the US in California. So thank you, Jill, for getting up early to speak to us today. Jill has had a long and distinguished career, and I think we would run over if I listed all the awards she has received. It is noteworthy, however, that Jill is, of course, a founding member of the SETI Institute. This is worth highlighting since the talk today is very much on that kind of topic. She began with a PhD from Cornell in engineering physics, a bachelor in engineering physics from Cornell and a PhD degree from the UC Berkeley. And then went on to work on NASA's SETI program. And when that was terminated, that's when she took things into her own hands and started laying the foundation for what has become the SETI Institute. So awards, which I will mention, which are maybe not entirely standard for an astrophysicist, are on the one hand, the 2004 Time Magazine Award for one of the 100 most influential people, and in 2012, one of the Time 25 most influential people in science. Other recent nominations involve Fellowship of the American Association for the Advancement of Science in 2002, Legacy Fellow of the American Astronomical Society in 2020, and then also a member of the American Academy of Arts and Sciences since 2021. Those of you who are interested in movies will know that Jill Tarter provided some inspiration for the movie Contact, though I suspect not for the way in which real-time data analysis was carried out on the radio signals. That was maybe a slightly freer interpretation. And also another piece of trivia is that Jill has an asteroid in her name. And I don't know whether those attributing the asteroid paid attention to that being, as Jill used wording in her abstract, habitable real estate, but I hope it is nevertheless in a pleasant part of the universe. So Jill, we are very much looking forward to your talk, which is called A Cosmic Perspective, Searching for Aliens, Finding Ourselves. And the microphone is all yours. Just for the audience, before you kick off, as usual, you can put questions in the chat during the presentation, or you can raise your hand at the end of the presentation. And when Jill is done, we will proceed to go through those questions, alternating between raised hands and questions in the chat. So Jill, yes, the stage is yours. Take it away.
Oh, thank you very much. It's really a pleasure for me to be able to talk to the SE audience about what I think could be this century's game changer. So let me do a little bit more of an introduction, because I'm really hoping that by the time that we finish with this session, I will have been able to change the perspective of at least some of the audience and have you look at yourself in another new way. So, oops, now it doesn't want to advance, and it did just before. All right, so my team uses radio telescopes to try and find evidence of extraterrestrial technologies. And I'm the one that's not wearing the headphones in this picture, right? The other one is Jodie Foster. So I have degrees in engineering physics and astrophysics, and my jobs with very many different titles over the years have basically been all about working on this question of, can we find evidence of someone else's technology? And indeed, although I am formally retired, if you asked me what I do, I would say that I am, in fact, the chief cheerleader for all things having to do with this search for extraterrestrial intelligence. And before we talk about finding them, I think it's important to put us into context. So where are we and when are we? So we're here, right? It's obvious. And for most of us, the past 2 years has been working from home, and hopefully that will change in the near future. And for me, that home is here in the Berkeley Hills on Shasta Road, in the in the western part of Berkeley, California. And that is in the Bay Area region near San Francisco. And from the altitude of low Earth orbit, I would see myself as being here on the west coast of the United States. And indeed, the really important thing, since 1968, when Bill Anders, an astronaut, took this Christmas Eve photo of Earthrise, we've been able to envision ourselves as being here. So this is really was our first opportunity to for a truly cosmic perspective. It changed how we see ourselves, and it became an emblem for the environmental movement in terms of providing sustainable future for all life on this planet. And this is a photo that was taken in the summer of 2013 by the Cassini spacecraft that was orbiting Saturn, and it turned around and it looked back and it saw us here, right? There is a little dot at the end of that arrow, and that is us. That is all of us in this Cassini selfie. And before that, in 1990, as the Voyager 1 spacecraft passed by Neptune, it turned around to image us as a pale blue dot in a sunbeam. And as we move back out, we're actually here in the boondocks of a large spiral galaxy, far from the center. Our sun is only one of about 400 billion stars in this Milky Way galaxy. And no, this is not an image of the Milky Way galaxy, because we have no way to get outside at the moment and take such a picture. It's an image of a large spiral galaxy that is what we think the Milky Way galaxy would look like if we could go take such a picture. And although we can't take a picture in the optical, we can in fact use radio telescopes to observe methanol and CO gases surrounding newly forming stars in order to map the Milky Way from the inside out. So after some 5,000 hours of radio telescope time, this recently published image map is the best estimate of what the Milky Way galaxy would look like from a distance. And you see, we got it pretty well like the image I just showed you. So that's where we're here, right? On this spiral arm of a beautiful spiral galaxy. And then when we look at something like the Hubble Deep Field images, we see that our galaxy is here. So all of those dots of light are not stars, but they are individual galaxies, each of which has hundreds of billions of stars within it. And as we look in detail, we see that some of those dots are fainter and smaller than others. And that's because they're farther away. And so this reminds us that as we look farther from our home, we are looking back in time. And so we now have to take in this concept of cosmic time. And so we're now, right? And that is some 13.8 billion years after the Big Bang that created the universe in which we find ourselves. And we need to think about these large timescales, long timescales that allowed for the evolution from the Big Bang to big brains, because we are really intimately connected with faraway places and long ago times. So this is a picture that is continuing to evolve. In fact, we've directly observed only about 4% of the total matter energy density in the universe. Cosmologists struggle with dark matter, dark energy, and gravity itself, right? So at the smallest scales and the earliest times, it's not yet possible to reconcile quantum mechanics and gravity. Still, this is the most self-consistent perspective of here and now that's ever been assembled, and one that we can expect will be subject to future self-correction. So we humans trace our lineage not just back through the centuries of our families, not just back through the millennia of human civilization with its art and its many experiments in governance. We trace our heritage not just back over the millions of years since we branched off from the great apes, and not just back the 2.4 billion years during which Earth's atmosphere has been perfused with oxygen, thanks to the photosynthetic labors of cyanobacteria, and not just back to the formation of the sun and our solar system 4.6 billion years ago. We've got to go back further, millions of years, to a giant molecular cloud that was contaminated with the winds of Wolf-Rayet stars and the debris of supernovae explosions and radionucleotides from neutron star collisions. The iron atoms in the hemoglobin molecules of your blood and the calcium in your bones and teeth, these elements were all fused, literally cooked up, deep within old massive stars that ended their lives in catastrophic explosions. We call them supernovas, that blasted off the outer layers of the star, leaving behind remnants, like this recent remnant that became incorporated into our solar system, just as this supernova remnant will be incorporated into future generations of stars and planets and perhaps life. So over 400 years or so of using telescopes, we have actually learned that it takes a cosmos to make a human. You owe all that you are and everything that you see around you to nucleosynthesis, the cooking of heavier and heavier elements from simple hydrogen that took place at the heart of a long dead star, end of its life. So quite literally, you are made of stardust. So if we are really intent on looking for life beyond this Earth, that's what astrobiology is all about. It seems to me that we should be looking for both biosignatures and technosignatures. We're actually trying to find inhabited worlds through the actions, either natural or intended, of the inhabitants of those worlds. And so this approach fits naturally together under an umbrella of a new-ish science that we call astrobiology. So finding life beyond Earth? Well, we could discover it with in situ biomarkers that we remotely observed from the Earth or from spacecraft. We could go looking for artifacts within the solar system, or we could look for remote biosignatures. So biosignatures. In the past 5 decades, NASA's been discussing missions capable of finding life by looking for biosignatures, the chemical fingerprints of life on planets and moons within our own solar system and in the atmospheres of exoplanets. The Viking lander was the first mission that showed us just how hard this is going to be. There are now a number of ground-based facilities and space-based missions on the drawing board. And the decadal review that has just been completed for the 2030s has been dealing with this question and trying to prioritize which missions are most likely to yield results in a reasonable timescale at a reasonable cost. And this is not a small project. These are going to have to be big undertakings because they just can't do their job otherwise. So if you look at the spectra that I show here for Venus, Earth, and Mars, you can see that Earth with its oxygen and O3 has a very different appearance and spectral characteristics than the planets such as Venus and Mars. And you want to go looking for these fingerprints of non-equilibrium chemistry, but from a very large distance. And you have to be willing to think about ambiguities and what could give you a false positive. So recently, we saw the announcement of the detection of phosphine gas in the cloud layers of Venus. And that was extremely interesting because on Earth, wherever phosphine is being created, it involves biology as a mediator. And Venus, by contrast with exoplanet atmospheres, Venus is right next door. And yet we still got this one wrong, right? It was only a single line detection. And in fact, it apparently attributed the spectroscopic feature to the wrong molecule. It's actually more likely to be SO2 than phosphine, right? So that just shows us how hard this is going to be, and the ambiguity that we need to be prepared to deal with. And I would claim that that ambiguity can be reduced if we decide to look for mathematicians rather than microbes. Right? And so that's what I've been pushing for decades now. There are other ways of potentially finding life closer to home than the exoplanets. We could, in fact, send missions to fly through the geysers that are erupting from the south pole of Enceladus. Right? And we could look at the chemical composition of what's coming out of those geysers, which we think are connected to deep underwater, surface oceans that are incredibly, perhaps, rich with biology, such as our own subsurface vents are on this planet. So how are we going to be able to unambiguously decide that any molecular fragments that our spectrometers might find in these plumes are due to biology and not just organic precursors? Well, as I've said, I think that ambiguity may be reduced if we decide to look for mathematicians rather than microbes. So when we talk about life beyond Earth, so we can discover it in situ biomarkers on bodies within our solar system, or artifacts in our solar system, or remote biosignatures in the atmospheres of exoplanets. But we could, in fact, also think about detecting the work product of any kind of life. We could look for deliberate technosignatures, or we could look for the serendipitous kinds of observations that might result as the result of very vast astroengineering projects. So we could look for technosignatures. And these searches face the same problems as searches for biosignatures, because they have to deal with false positives and with the difficulty of conceiving and building instruments to find what we don't yet know. But nevertheless, despite these difficulties, I think this type of research absolutely belongs within the portfolio of searches for life beyond Earth. So when you're talking about technosignatures, looking for signals that would indicate somebody else's use of technology, I think there can be two kinds of deliberate signals that might be produced by another technology. There are signals that are almost natural in their appearance. And then there are signals that could be instantly decided to be obviously engineered. So what about almost natural signals? Well, we found pulsars decades ago, and somebody talked about little green men. And we found pulsars that have stark waves and change their moment of inertia. So they go from one period to another period. But we've never found a pulsar that goes from period 1 to period 2 and then back again to period 1. But you could imagine that is something that could be engineered and would show up in our databases of pulsar searches, and some graduate student at some point would say, huh, what's going on here? And we might, in fact, detect a technosignature that way. Here's another idea, right? We are looking at, we find exoplanets without actually seeing them directly by the transit method. So we see that when a planet passes in front of its star, from our point of view, that the light of the star is dimmed. And the IAU tells us that by definition, planets are spherical and their shadow across the planet will be a circle, right? But in fact, you could imagine constructing artificial structures to create transits. And these structures would not be spherical. They would have some distinct shape. And in the high order moments of the luminosity or transit curves, you could detect shapes that were non-spherical. And so you could, in fact, perhaps find these artificial transiting elements. Or here's another one. So there are stars, variable stars, that increase their size and therefore their luminosity with time, and then collapse down to an initial smaller size. and then do this all over again. So you have periodic Cepheid variables. Now, suppose you're an advanced technology who has one of these somewhere close by, and you decide to orbit some sort of neutrino factory around the Cepheid. And then you wait, and as the star is in its collapsed phase, the atmosphere of the star is in its collapsed phase, and is thinking about expanding again, you zap the stellar atmosphere with your energy source, your neutrinos, and you make it expand prematurely. And now what you've done is created a Morse code system. So the Cepheid has its normal period and it has a shortened period. So it has a dash and it has a dot. And this Morse code system could be in fact seen beyond our galaxy out to the Virgo cluster of galaxies. And so now you've created an information bearing signal that can be modulated. Okay, not by us, but by an advanced technology perhaps. So those are things that are almost natural that would get captured in these nets that we cast to make surveys of the sky and what's going on. And more, we're making those surveys with temporal resolution, looking for things that change over time. So almost natural. All right, what about obviously engineered? Well, we could look for frequency compression. We could look for a signal that shows up at a single channel, single frequency on the radio dial, because nature can't do that, but technologies can. We could also look for a signal that is compressed in time as well as frequency, perhaps. So a single nanosecond pulse of an engineered laser. And then we could also understand the nature of the engineered signal because it would be monochromatic, only at one frequency, like a laser. So it's important to think about all these different types of signals because they have different consequences, right? For the signals that are almost natural, what you should do is do astronomy in any way you can with any new instrument that you can think up of, and look at the sky in new ways and be mindful of things that go, oh, what's that? But in terms of these obviously engineered signals, you need to think about building dedicated telescopes and using them systematically to conduct a search. And the reason that you need to think about it in a different way than the almost natural signals is because astronomers will not be building your tools for you. Right? You can think about all kinds of experiments that could, and instruments that could be piggybacked on large optical and infrared and radio telescopes for these almost natural signals, but simply because the obviously engineered signals don't appear the way nature appears, you're going to have to build those systems yourself. And that's where we're beginning, or we have been going for quite some time now. So within NASA, SETI got started in about 1975. First SETI search was done in 1960 by Frank Drake from the National Radio Astronomy Observatory. But within NASA, got interested in this field in about 1975. And so we did what NASA always does when it's looking at a new field of endeavor. We held workshops, in this case at NASA Ames. And there was within that workshop a working group that was formed that tried to answer the question, or thought about answering the question of, are there planets? around other stars, because in 1975 we hadn't a clue. And so actually out of this workshop for SETI research came the first ideas of how one might observationally find planets around other stars. We published the results in something called SP419. As a result, Senator Proxmire awarded NASA a Golden Fleece Award for wasting taxpayers' money. And ultimately, on Columbus Day of 1992, NASA got serious enough and had raised enough money from Congress to launch a 10-year program called HRMS, the High Resolution Microwave Survey. And we intended to do both a sky survey and a targeted search of exoplanets. A year later, to the day, the search was terminated by Senator Bryan of Nevada, and we had to go into a different mode of raising funds privately to conduct this search. And so we commenced a 10-year program that we called Project Phoenix, which was rising from the ashes of congressional termination. And one of the things that we did is to publish the results of yet more workshops when we sat down to say, okay, how are we going to do this with private funding? And we published something called SETI 2020, what we should be doing for the next 20 years, a roadmap. First of all, it said, look, this is the 21st century, just about, and we should be expanding our wavelength coverage. We shouldn't be just doing radio searches. We should be expanding our search into the optical and the infrared. And we should build our own telescope so that whereas we had been able to get 10 or 15% of observing time on other large telescopes, primarily radio at that point, we needed an instrument that we could have use of 24/7. So we should build a SETI dedicated telescope. And then because we were cognizant of the fact that some of the signals that we were looking for might be transient. And that meant that in order to find them with any probability, you needed to be looking at all the sky all the time at all frequencies. Big job. We've gotten the first two bullets started, but now 20 years later, 20 plus years later, we're just beginning to work on that last piece about finding transients, because for decades, we really haven't had any reliable sensitivity for transients. All right, here is the telescope that we've built. It's called the Allen Telescope Array. It's in Northern California. It consists of 42 6-meter radio telescopes, dishes. Ultimately, we had hoped to build this out to 350 dishes, but there was so much R&D that we hadn't yet completed when we started to build this, that in fact, our money only covered 42 telescopes. And we are using these daily to look for SETI signals. So it's an interferometer. It has very wideband receivers, so we cover from 1 to 10 gigahertz. That factor of 10 is huge compared to the usual 10 to 20% bandwidth coverage of delta lambda over lambda that a normal telescope would cover. And because the dishes are small by design, they have a very large field of view. And because the dishes are spread out on the ground, they have very high spatial resolution. So this is the SETI telescope that has been built at Hat Creek in Northern California in a partnership between the SETI Institute, UC Berkeley, and private funders. So the spatial and spectral coverage of this are astonishing, right? Here's the moon on a scale with the Andromeda galaxy. And so you can see that the moon is 0.5 degree across, the galaxy is 2.5 degrees across. And if you think about what was our largest telescope at the time, the Arecibo telescope in Puerto Rico, which sadly is no more, you can see there the field of view of that large telescope is tiny compared, even if you put multiple focal plane elements, detectors, in the telescope, you can see that it's still tiny compared to the field of view of these small telescopes. And because it's an interferometer, we actually make a radio camera that has about 1,250 pixels and about 1,024 different spectral channels, colors. So it's a wide angle radio camera, which can work in a snapshot mode. You don't have to let the Earth rotate in order to get your picture because you have so many elements. And the other thing that you can do with this is, if you have enough computing, you can actually phase up the array so that it looks at individual small resolution elements or beams on the sky. In the case of the ATA, we built a beamformer that could look at 3 beams simultaneously. We're now moving on to 64 beams. But the really nice thing about being able to phase the array up into these multiple beams is that it helps you discriminate against interference. And indeed, if you have signals that are predictable and you know are going to be coming into your field of view and spoiling your image, your radio image, you can in fact do a little bit more mathematics and null a particular spot on the sky where that interfering source might show up. So we can do active nulling to help us discriminate and get out of our data sources of interference like 65,000 element constellations of low Earth orbiting satellites. So when we started to observe with this back in 2007, there was something called the HabCat that I had built with a graduate student, where we took the information that we had on nearby stars and predicted which of those might be suitable hosts for habitable planets. Then when we began to get the results from Kepler and other ground-based telescopes about known exoplanets, those became our target list for observations. And now, since we know, as the result of our studies of exoplanets, that every star has at least one planet, statistically speaking, we now choose our targets by using the closest targets and moving out. So we do that. We choose our targets that way. You can see right ascension and declination. It's our map of the sky. And it, this was 2017, so a while ago. You can see the number of targets we had looked at. You can see a couple of other things in that picture. You can see that we spent a lot of time looking at the stars that Kepler showed us had exoplanets. So there's a blob to the right of the bigger blob, and to the left you see not much coverage, because we spent, whenever that declination was available, we spent the time looking at the Kepler field, and that left the rest of the declination strip fairly unobserved. That's now changed as we have changed our strategy. But the thing that hasn't changed is, if you look below 0 degrees declination, there is a strip that is unobserved. And that's because that is the geosynchronous belt of satellites. And those are incredibly loud and very damaging to our very sensitive receivers. So if you want to look at directions in the sky that are within the geosynchronous belt as we look from the northern hemisphere, you actually have to go to the southern hemisphere and squint up under that geosynchronous belt. And we've done a number of observations that way at telescopes in Australia. So that's what we've been doing with the Allen Telescope Array. But now, over the past 5 years, there has been a game changer. And that's a pledge of $100 million over 10 years from Yuri Milner to build instrumentation for existing telescopes in a big way. So this is the project called Breakthrough Listen, which is now the 900-pound gorilla in this field. And they have built instruments for the Green Bank Telescope in West Virginia. They have built instruments for the Parkes Telescope in New South Wales. And they have built optical instruments for the Planet Finder Telescope at Lick Observatory here in Northern California. And they had plans and are in the works, various stages of realization for building instrumentation for the Large Fast Telescope in China, for the Meerkat Array in South Africa, and for the Jodrell Bank Telescope in the UK and the Maryland Array that's associated with that. So that's the Breakthrough Listen project. And there are other SETI programs on the telescope today. SETI at Home was using data that was collected at Arecibo and recorded and then sent out to citizen scientists who were using their own computers to analyze the data. Sadly, of course, as we lost Arecibo, we have lost that capability. There is the LOFAR array in the Netherlands and the UK, low frequencies for doing SETI now, as well as the radio astronomy that it was intended to do. So SETI is a parasitic search, a commensal search with LOFAR. There's a 64-meter telescope in Italy called, and SETI Italia is happening there. There is a sky survey that is now being conducted by students associated with the Goldstone Apple Valley Radio Telescope down next to the Deep Space Network in Southern California. They moved one of the telescopes outside the fence. And so there is now this teaching capability, and students there are actually conducting a sky survey the way that JPL had intended to do as part of the NASA high resolution microwave survey. And occasionally there are these campaigns where we get multiple telescopes at multiple frequencies in multiple countries to observe the same part of the sky simultaneously, looking for engineered signals. What's coming up is a project called Cosmic, and it's being spearheaded by Andrew Simeon. And it takes the most productive radio telescope that we've ever had, which is the Very Large Array in Socorro, New Mexico. And it is, in fact, splitting the voltage output from each of those telescopes and sending the data to a new series of signal processors that will be looking for SETI and other projects that have been proposed for looking at the sky in this way. And it's great because it's commensal. The radio astronomers who observe as a result of observation proposals. They get their data unimpeded, but we get data that we can observe and process in a different way for SETI. And then there's optical SETI, which has taken off. Here's a student-built project at Harvard that did a sky survey many times, looking across the sky. The data from the Keck Observatory, the high-res instrument at the Keck Observatory, looking for exoplanets, can also be reanalyzed, looking for engineered signals. There is a small, dedicated, private observatory in Panama, the Buquete Optical SETI Observatory, that looks for SETI signals all the time. And then there's a lot of data mining. So, for example, Penn State has been looking at the WISE infrared spacecraft data archives, looking for Kardashev type 2 and type 3 civilizations. These are civilizations, technologies which have the ability to capture and use type 2, all of the power coming from their host star, and K3, Kardashev 3, all of the power that is radiated by their host galaxy. And now there are new SETI projects for optical that are being worked on today. The first one is Veritas. This is an array looking for high energy showers in the atmosphere that exists. And what we did is not to build a new instrument for these 4 telescopes, but simply write new software, because the telescope was sensitive. These telescopes were sensitive only to long trails of air showers. But we wrote software that can now look for single pixel events. So each of these telescopes has an array of about 500 photodiodes in its focus. And we wrote new software so that we could, in fact, find single pixel events, the same pixel on all of the telescopes for the same piece of sky that might be indicative of a SETI signal. Shelley Wright at UC San Diego and Paul Harwitz at Harvard are collaborating on something called PanoSETI. Can imagine building a Buckminster Fuller kind of dome, and in each of those hexagons, you put a half-meter Fresnel lens. You can see Shelley imaged behind her Fresnel lens, and that lens can focus a large piece of the sky down onto a very sensitive photon counter, or an array of photon counters. And so with something like 126 of these lenses on a geodesic dome, you can look at 10,000 square degrees of the sky at the same time, all the time. And of course, you have to build 2 of these because, and you want them to be about 1 kilometer apart, because you want to be sensitive to transients. And the only real gold standard for knowing that it's a transient and not a problem with your hardware or software is to have 2 of these instruments looking at the same piece of sky simultaneously. So that's an ongoing project at Lick. It's been delayed because of COVID-related problems, but it is on the way. At the SETI Institute, we're not building observatories, we're building cameras. We're using high-grade optical cameras and grading, very good gratings and very high time resolution readout, again, to look at all the sky that is above the horizon. And these, this is the first installation at the Ferguson Observatory in Northern California in Sonoma. But ultimately we hope, and the second installation is at Haleakala in Hawaii. Ultimately, we hope to have something like 12 sites around the world. You can see that map at the bottom. And this way you can look at all the sky all the time, looking for transients, as SETI 2020 told us we should. So in the future, well, JWST is up there now, and it's going to do a lot of observations on exoplanets and their atmospheres, and we'll see what we can find. The Roman telescope is going to launch. HABEX, in fact, will be doing a lot of exoplanet work, and LUVOIR, right? Large ultraviolet optical infrared telescope may be something in our future if we follow the recommendations of the decadal. And this may be something that is ultimately large enough to collect enough photons that we could actually begin to look for this non-equilibrium chemistry in the atmospheres of exoplanets. Ariel, and here's a strange looking telescope. It looks like a cross between a radio telescope and a Ferris wheel. It's been proposed by people in Hawaii. And the idea is that if you track an exoplanet through enough orbits, you can in fact deconvolve those signatures to actually make an opacity map of the surface of the planet and distinguish between continents and oceans. And this may be something that ultimately gets funded. And further in the future, you have the 30-meter telescope and the Magellan telescope and the extremely large European telescope and LSST to give us a synoptic look at the sky, looking for these transient events every few days. Laser SETI, we hope. Pano SETI, we hope. Veritas is, in fact, on the air. And then instruments on FAST, the Chinese telescope, and ultimately Meerkat and the Square Kilometer Array. And perhaps the next generation VLA, cosmic squared kind of approach. And then if we could get that Exo Life Finder to work, we could expand it to something that's more like 80 meters across. And in fact, if you could do this, this would be sensitive enough to see the heat signatures of cities and clusters of technology from nearby exoplanets. So ultimately, the day Square Kilometer Array, and maybe having as many as 250 beams on the sky at any one time. And the sensitivity eventually to be able to see the kinds of powers that technology such as ourselves generates. And to date, we continue wherever we observe to fly the flag of Earth as an indication that this is an endeavor for humanity and not for any particular country or nation state. And we also always still plan for success. And we have champagne on ice wherever we observe. Look forward to drinking that champagne someday. Of course, the problem is getting harder because the interference that we generate with our own technologies becomes more and more difficult, and more of our computing cycles have to be spent trying to mitigate this interference. So the technologies that we use for the search have changed greatly since the first search in 1992, that NASA search. And we expect this to continue. We will use whatever technologies are available and affordable. And over the time since that first search in 1960 by Frank Drake, when we asked, how much searching have we done? Well, if you take the 9-dimensional space that represents all of the different parameters that you might have to get right in order to find a signal, and I set the volume of that 9-dimensional space equal to the volume of all the Earth's oceans. When SETI turned 50, we'd searched 1 glass of that cosmic ocean. Now at 60, it's more like a small pool or hot tub, right? So things are getting better, they're getting faster, and that will continue. And it isn't just Moore's law, right? We're getting better faster than just Moore's law, because there have been parallel improvements in many of the components of the system. So we are now having dedicated telescopes and more telescopes at more wavelengths and more time on the sky via commensal observing opportunities. And we have improved algorithmic and machine learning searches for signals. So the other thing about life beyond Earth that we shouldn't forget is that we, in fact, may end up exporting it, right? So Moon, Mars, the asteroids, we've talked about all of that, and Breakthrough Starshot and the 100-year Starship study and Icarus are talking about interstellar missions where we may send humans to nearby stars. If we have a long enough vision, we can imagine that that may be the way that life moves beyond Earth. We export it. And I think it's really important to talk about these kinds of ideas to as large an audience as we possibly can. Because I think if you get someone to think about life beyond Earth, what might it be like? How different it will be from life that evolved here on this planet. It has the effect of holding up a mirror to your audience and saying, look, in that mirror, compared to something else that might be out there, we are all the same. And this view, this point of view, this cosmic perspective is incredibly important because we have all of these challenges on this planet if we want to have a long future for life. And those challenges are not going to be solved nationally. We need to cooperate globally to meet those challenges and to find solutions. And so changing our point of view, changing our perspective is incredibly important. And Caleb Scharf has said it very well. He says, on a finite world, a cosmic perspective isn't a luxury, it's a necessity. So that's my story, and I'm sticking to it. Thank you.
Thank you very much, Jill. What I did not mention in introducing Jill was that she has a long record and an acclaimed record of public engagement and cares deeply about education as well. And thanks for treating our audience to another example of an excellent talk. So we have quite a few questions that have come through in the chat, which will give us an opportunity to revisit some of the many things you told us over the last hour. I'll start with a question on the chat, but just to remind people in the audience, if you want to raise your hand and ask a question in person, that is also perfectly fine, and I'll just call you up, alternating with questions from the chat. So yeah, let's go back to the start, more or less in the timeline of questions that came through. So Terry Mosley asks, and Jill, I don't know if you can see these questions on the chat as well, which might make it a bit easier for you rather than just listening to me. So for the audience, I'll read this out. How early in the history of our galaxy could a planet with the right mix of elements to support advanced life have formed in the habitable zone of a roughly sun-like star? So yeah, thinking about when conditions not too far away from us might have been suitable for SETI signals to be produced.
Actually, quite a while ago, because we're a very young star in our particular neighborhood. most of the stars around us are 1 billion years older. So there could have been favorable conditions billions of years ago.
Okay, I'll take another one from the chat before we go to the first raised hand. So I'll actually merge two questions here, and you can probably refer to some of what you've already said, but there were two questions on how SKA and or JWST can be game changers or not in the SETI search.
Well, JWST will give us an ability spheric analysis looking for non-equilibrium chemistry for stars in our immediate neighborhood. The square kilometer array will in fact extend our ability to look out into the galaxy in much larger volume, looking for these engineered signals. So they are game changers. And we have a wonderful history in astronomy, which says that we go to our funding agencies and we say, we want to build a new telescope and it's going to do X, Y, and Z and answer all these questions. And then we have been blessed by the fact that what this new telescope looking at the universe in a new way does is show us something that we never expected, right? And so we should be prepared for learning things that were not on our bullet list, our bucket list.
Planning for serendipity.
Yes. And it's really hard to sell that, right?
Okay, so Will Wall has raised his hand and has also pointed out the risks of doing high order polynomial subtraction for analyzing Venus spectra, but I guess Will's question might be about something slightly different. Will, please.
Hello, can you hear me?
Yeah.
You can.
Okay, great. Yeah, I mean, I really enjoyed your talk, especially at the beginning and at the end where you put us in our place. That was very appropriate, I thought. I'm going to ask you a speculative question. I think it's a variation on a question you received before, because you're talking about detection using electromagnetic waves. I can imagine an advanced technology might use something like gravitational waves, modulate gravitational waves, or neutrinos, which have the advantage that it doesn't matter if the source has risen or set, which they've just passed right through the Earth. So that would be a great way to communicate. Do you think there may be some advantage in SETI people learning about the next generation of, or maybe even developing the next generation of neutrino detectors, gravitational wave detectors?
I wish the SETI community had a budget that would enable that kind of development work. And yes, you're correct. We're looking for electromagnetic information. It's because it's what we can do with what we can afford. I think that in terms of building instrumentation that could be sensitive to gravitational waves or neutrinos, we need to find a way to do it commensally, because we're never, well, maybe in my wildest dreams, we would have a budget to build dedicated instruments for SETI in these multi-wavelength modalities. But so we talked to the folks at IceCube, right, that are looking for neutrinos in the ice of the Antarctic. And we talked to them about, let us know about anything that looks strange. And the gravitational folks at LIGO, well, lots of things look strange because this is such a new science. But yes, we think about it, but in terms of implementation, we have to, at the moment, depend on others. So, right. I will absolutely fess up that we may be looking with exquisite precision for exactly the wrong thing.
Right.
So, yeah, just
keep an open mind. So that's great. Yeah. Okay, well, thank you.
Thanks, Will. So next, I want to combine two questions from the chat, one from Vladimir Irapetian and the other one from Parvin Hovaida, both to do with searching more in the megahertz range. So on the one hand, one question was, how about doing such a search from the moon, basically, where Earth-based problematic signals or interference is not as serious. And then more specifically, that is then the second part of the question, which comes from Parvin. Well, if you look at megahertz frequencies, that would be precisely the kind of frequency where astrophysicists might look for host star-planet interactions anyway. So a natural process due to magnetic field configurations, as far as I understand. So yeah, could that be a double winner, so to speak?
Yeah, so it might be another opportunity for commensal observing. The problem that we're facing at the moment is, yeah, the lunar far side is the only place in the solar system that never has the Earth in its sky, right? So you get away from all of the Earth-centric interference that's being generated. On the other hand, look at what we're planning to do. We're planning to build Gateway, right? Or some other structure like that right above the lunar far side. And we will be building our, we will be fouling the nest and electromagnetically speaking up there. So what we've been talking about is making sure that any structures, so you can't, can you make them less light reflective? And can you arrange that any comms that are put there are multiple frequencies, so that at least at some time you can look at one frequency, right? Because you will be using the other frequencies to still get a view of the sky. Yeah, it's a problem. I mean, there are lots of people who want to be there for lots of good reasons. And so we, just as the lights have been creeping up the mountainsides at optical observational sites, so now we are beginning to think about doing things that will make the radio quiet far side of the moon much less quiet.
Yes, lots of not only questions, but also appreciation coming through on the chat. We can take a few more questions before we wrap up. So I'd like to take this one from Rudy without surname. So Rudy asks, what is your opinion about the Fermi paradox? Does it reduce the probability of finding something and get SETI successful?
Okay, so the Fermi paradox, I could phrase it this way. If there had ever been anywhere or any when another technological civilization, then given our history, it would be a very short time between the start of their technology to them becoming spacefaring civilizations. So short on cosmic timescales. But we don't see them. They're not here. And therefore, the only way to explain that is that there can never have been anywhere or anywhen another technological civilization. We're the first. My problem with that so-called paradox is that it's hardly a paradox. If you've only looked at one glass of water out of the cosmic ocean that you might have to explore in order to find a signal or evidence of someone else's technology, you can hardly say they're not here. So we just haven't observed enough for me to be bothered and to think that this is a paradox.
So this leads on nicely to the next couple of questions I want to take from the chat. The first one being from John B. Grenfell. If SETI 60 covered, you said, the small pool in this case, in an ocean of the 9-dimensional parameter space, what will the new quantum computing factor 160 million increase expand this number to? Yeah, basically the bottom line, I guess, what will it take in terms of not only hardware, but also data analysis breakthroughs? And we could also maybe follow up with where should most of the funding go for SETI research? Should it go to software development in the future, to analyze commensal data streams, or something else? So yeah, a few aspects there, which maybe you can briefly reflect on.
Quantum computing is going to put us on a different exponential, right? There's going to be a real, we're not just going to continue on the same exponential improvement. We'll be on a different curve. And in terms of where should the money go, I've been thinking more recently about the fact that we should be, we'll use commensal observing wherever we can. But when we are building our own instrumentation or thinking about how to observe in the future, we need to be thinking more about techniques that will be verifiable and credible, right? So there are, and it's, in the radio, and actually even in the optical and the infrared, interferometry is a really good way of making credible observations, even of transients. So building your detectors so that you can believe the results is something that I think we should be investing in.
Okay, let's take two more before we close. This one's from Orcadian. Have we detected any unexplainable signals at all at this stage?
Well, you've probably all heard about the WOW signal. That's usually the one that's flagged as the most interesting potential SETI signal that's ever been detected. If I'd been running that program, you would never have heard about the WOW signal, right? Because what you need to do is set a certain criteria or set of criteria for what will constitute a particularly credible detection. And in the case of that telescope, the Ohio State Telescope, which is a transit instrument, what they did is they built two receivers. What they expected to be a SETI signal would be a point source moving at sidereal rate. So it would go through the east receiver and then fade away, and then show up in the west receiver and fade away. It didn't do that. It showed up in one of the receivers. They don't know which one. I mean, we had hardly any computing at the time. And it did not behave and pass the tests that the observers had set out in advance. And I think that it isn't fair to change the rules after you start. If you have a set of criteria and you're going to say this is what is going to be a credible signal, then the signal has to pass those criteria. And so it didn't. We have thrown away gazillion signals. And at least in the SETI searches that I've been part of, because we do them in near real time, we immediately follow up on signals that trigger the thresholds that we've set. And in those cases, we've either been able to see in multiple beams that we see the same signal in more than one beam, or that it never recurs. So we have a minimum floor of minutes for how long the signal has to persist. As we get into this new phase of transient signals, I think the only thing there that will allow us to have confidence is that we have multiple sites that detect the same thing. So yeah, we've thrown away a lot of signals. I may have thrown away a real SETI signal, no question, but we've required that they pass the thresholds and the criteria that we've set.
Okay, so we won't be able to take all questions, but I'd like to ask one more, and maybe again sort of combine various general questions that were posed in the chat in doing so. So this one is from Eckhard Stürmer. Assuming alien civilizations will make the same mistakes as us, they might spoil their night skies with light pollution, perhaps detectable by unusual spectral signatures. Or yeah, I get another chat comment said, well, they might have lots of satellites in a geosynchronous orbit, making a lot of noise. So any chance of detection? And I guess somewhat related to that, you showed us the map of RAN DEC and where you have looked. That was that map with the red dots where you had pointed out the Kepler field, for instance, which had been targeted preferentially at a certain DEC. I was struck by the fact that you didn't have your band of the Milky Way running across that. So apparently it's not the best strategy to just look in the Milky Way, but I guess that's because lots of the potential targets are closer by and the Milky Way structure it doesn't show up in that case. So maybe you can briefly reflect on, where best to look nearby, and would such signals be loud enough, such human signals like airport radars or geosynchronous satellites?
Okay. There actually have been some papers that have written that have actually thought about a geosynchronous belt on steroids, right, from an advanced technology and what that might look like, and how you would distinguish it. In terms of where to look, you're actually right. We haven't looked far enough to see the structure of the Milky Way. We're really talking about things that are very close by. And so I think it's still a good idea to try and have this two-pronged strategy that NASA envisioned for the high resolution microwave survey, which is a target search where you use information that you think is relevant to whether or not a target might host a habitable world. And then you say, I may be totally wrong. I may not be thinking about this in the right way at all. So let's look at all the sky. And I think both strategies are relevant, and we're trying to do both. And now, again, with the ability, at least in the radio, not yet in the optical or infrared, with the ability to have a focal plane array or be able to form many hundreds of beams simultaneously on the sky within your field of view, you can begin to do that. And that's what I look forward to in the future.
Thank you very much, Jill. And again, also conveying that same message, which has come through the chat. Thanks from many of our participants. Sorry to those of you whose questions we couldn't bring up explicitly anymore. But remaining thing for me to do is to point out that same time, same space next week, we'll have the next Game Changer seminar. So looking forward to seeing many of you there. And Jill, it's been a pleasure. Thank you very much. And have a nice evening or nice rest of the day, everyone.
Okay, thanks very much. Bye-bye.
Bye-bye.